Hello everyone. I hope you are all in good health and safe. So I'm glad to be a part of this conference on physics education and research. My name is Raj Panchal. In my undergraduate study, I've done my BSc specializing in physics, and very soon I'll be doing my master's specializing in astronautics and space engineering at Cranfield University. Today I'll be giving a talk on bizarre black holes. So black holes are very much intriguing and it has interested a lot of people. So the highlights of my talk will go this way. We'll start with history of black holes, some basic concepts, death of stars, possible fate of stars, structure of black holes, escaping from a black hole, sun as a black hole, some recent discoveries, and some facts and references. So starting with the history of black holes, John Mitchell in 1783 was the first to describe an object whose escape velocity exceeded the speed of light, and they called it dark stars. The first ever black hole to be discovered was Cygnus X1, and it was detected by British astronomers Paul Murdin and Louis Webster in 1964. So, as the name suggests, Cygnus X1, because it is in the Cygnus constellation, the Cygnus is a swan basically, the X because it is a X-ray source, and 1 because it is one of a kind. So Karl Schwarzschild applied some mathematical calculations to Einstein's general theory of relativity and was the first one to theoretically demonstrate black holes. The name black hole originates from a prison in Calcutta, India. So in order to understand black holes, you need to understand certain basic concepts of relativity. So Albert Einstein in 1915 put his paper of general theory of relativity, and basically it predicts that space-time is curved. Objects like sun, earth and other planets tend to warp the space around them. This warping of space around the sun results in motion of earth and other planets around it in elliptical orbits. So as you can see in the photo over here, this is the sun, this is the earth. The green grid lines that you see is nothing but the fabric of space. So due to the mass of the sun, there is a depression caused in the space-time curvature. So as you can see, it leads to the curvature. It creates a depression. So higher the mass, higher is the depression. So what happens basically is in our solar system, all the planets, including the Earth and the asteroids, are falling towards the center of the sun. Basically, they are all in a state of free fall, falling towards the center of the sun by the force of gravity. And this is what Einstein predicted. The warping of space around celestial bodies depends upon their mass. Higher the mass, higher is the warping of space. Black holes warp space-time to a significant extent. Black holes have an immensely high gravitational pull. Not even light can escape from this gravitational pull. So in the photo over here, you can see the warping of space by the sun. This is the space warped by a sun. This is the space warped by a white dwarf star. This is space warped by a neutron star, and as you can see, the space warped by a black hole. So it is higher than these three, and it is very much high. So now, just like humans, stars also have a certain lifetime. So black holes are the result of a dead star. When a star dies, it has different fates. So in order to understand black holes, we need to understand first how do stars die. So just as we have a process of living, stars rely on the process of nuclear fusion to survive. So nuclear fusion is a chemical process by which two atoms come together, they combine to form heavier atoms. So this is the process by which stars live. So what happens in the star is, let's consider the sun. In the photo you can see the sun. So what's happening in the center of the sun is there are elements like hydrogen, helium in the center of the sun. So what's happening is elements are fusing to form heavier elements. So this is the elemental hierarchy that is going on in stars. So we have hydrogen, helium, carbon, oxygen, neon, magnesium, silicon, and iron. So what happens is, starting from hydrogen, the elements get heavier and heavier and go up to iron. So basically, when it comes to iron, iron is the dead stage of a star. So when it comes to iron, when a star is only left with iron, its life is about to end anytime. So what's happening in our own sun right now is there are two forces acting on the sun and keeping it stable. So one of the forces is the energy released from the nuclear fusion. The nuclear fusion is acting in the center, so energy released is in outward direction. So one energy, the force released due to the energy is acting in the outward direction, and at the same time, the sun has a mass. So basically, it has its own gravity. So this gravity is an attractive force, and it is trying to bring the surface to the center. So what's happening is the force arising due to the energy released due to nuclear fusion is acting in the outward direction, and the force due to gravity is in the inward direction. So these two forces balance each other. So this is what we call hydrostatic equilibrium. Our sun is in a state of hydrostatic equilibrium. So as long as we are above iron, there is no such problem. But what happens is when a star reaches iron, the energy released in nuclear fusion of two iron atoms forms a heavier atom. The energy is not that high to overcome the force of gravity. So what happens in that case is gravity becomes dominating, and the energy released due to nuclear fusion is not sufficient enough to overcome it. So basically, the gravity tries to shrink the star into a smaller size. So the outer part of the star goes into a supernova, and the inner stellar corpse of the star keeps on shrinking. So this is what happens. Now, possible fates of a star. So the first possible fate is a white dwarf. So white dwarfs basically have a mass of one solar mass or less. So basically, a solar mass corresponds to the mass of the sun, which is around 2 times 2 into 10 to the power 30 kilograms. They have extremely high density of the order 10 to the 9 kilogram per meter cube. They are extremely hard to detect due to their small size. Eventually, in about 5 billion years, the sun will turn into a white dwarf. Nearest white dwarf is Sirius B. It is found in the Sirius constellation at around 8.6 light years. So eventually, the sun is going to end its life. It is not soon enough. We don't need to worry about it. It is in the next 5 billion years. So it will end its life and turn into a white dwarf star. The second fate of a star is a neutron star. So neutron stars have masses corresponding to 1 to 10 solar masses. They can range between any of these. Neutron stars are supernova remnant of massive stars. So as I said, the outer part of the star bursts into a supernova. Extremely small radius of the order 10 kilometers. Neutron stars are extremely small. They are composed almost entirely neutrons. So what happens is the electrons and protons have an interaction due to the weak forces, and they turn themselves into neutrons. So neutron stars are almost entirely composed of neutrons. They have immensely strong magnetic fields of the order 10 to the power 11 Gauss, which is very much high. Ideally, mass of neutron star is almost equal to 3 solar masses or less. So the third and the last fate of the star is a black hole. Black holes have masses corresponding to 10 solar masses, ranging from 10 solar masses to 10 to the power 9 solar masses, which is approximately a billion solar mass, and they can be higher. So black holes are basically voids in space-time with almost infinite density and gravity. Initially, they were called totally gravitationally collapsed objects. Black holes do not have any independent characteristic except charge, mass, and spin. So if you want to define a black hole, you have to define it in terms of these three parameters: charge, mass, and spin. Just for your information, the first ever black hole, Cygnus X1, ranges in this mass range only. It is approximately 15 solar masses. So it lies in this range, but it is a low mass black hole. So these are the classifications. 1 solar mass or less corresponds to a white dwarf. 1 to 10 solar masses may lie in the neutron star range. 10 to 100 solar mass are black holes, but they are low mass black holes, and so they are given a name, stellar mass black holes. Then there is 100 to a million solar mass intermediate mass black holes, and we don't know much about these intermediate mass black holes. We don't know much about these because they are not very much found yet. And greater than a million solar masses comes the supermassive black holes. Now, understanding the structure of a black hole, the singularity is a center of black hole with infinite density and gravity. Second is the event horizon. Event horizon is the boundary of the black hole and it is the point of no return. Accretion disks, they are collection of gas, dust and matter particles spinning at almost the speed of light. Then there is a photon sphere, which is a region around the black hole where gravity is so strong that photons are forced to travel in circular orbits. So in the diagram over here, you can see the central part is nothing but a singularity. The black boundary that you see is the event horizon. The blue shiny thing over here represents nothing but the accretion disk. Okay, so in order to study black holes, these are the basic parameters in which we talk. Now, accretion disks. So if you have seen Interstellar, you must have seen this black hole. It's not a real black hole. It was called Gargantua in Interstellar. So in astrophysics, accretion is the process used to determine the motion of gas and dust being collected together by gravitational forces. Accretion is a process by which black holes are fed. Now we'll see that in the next slide. Particles in these disks experience a force of viscosity. So what happens in these accretion disks is a matter particle falling towards the black hole does not go through the event horizon straight away. What happens is it initially moves around in these accretion disks and eventually it starts falling inner and inner, and after a certain amount of time it passes the event horizon and it is lost forever. So understanding accretion disks is really important to understand black holes. And in order to spot a black hole, you need to spot its accretion disk because it is the only glowing thing that you will see around a black hole. Now, what is this glow? This glow is due to the temperature. The temperature of these materials falling towards the black hole is more than the temperature of plasma. So what happens is, this is explained by the term viscosity. So viscosity is the force experienced by matter particles lying one over the other due to the rubbing or frictional forces between them. So when two matter particles rub over one another, they develop a force of friction, and this leads to a force of viscosity. So due to this viscosity, the matter particles falling towards the black hole tend to heat up, and this is why it produces a glow. The temperature of the accretion disk is around millions of Kelvin. Now, how do black holes feed? So this is a photo of the Cygnus X1 black hole. This is a Cygnus X1 black hole, and this is a star orbiting it. So basically, it is a binary system. So it's not a real photo; it is a simulation, but it will help you understand how do black holes feed on the neighboring stars. So the stars tend to shed a lot of their mass through two processes. One of the process is stellar winds. The star throws away or spits a lot of its mass in the form of stellar winds, and the another process is Roche lobe overflow. So what happens is, due to the gravity of the black hole and the star orbiting it in a binary system are both entangled together. So the black hole sucks some of its mass, and this mass goes around the accretion disk of a black hole. So starting with the stellar mass black hole, eventually the black hole starts feeding on the star and its mass increases as it keeps on feeding matter from the star. So in such systems, eventually the star loses all of its mass and the black hole grows in size. So this is how black holes primarily feed in a binary star system. Now, black hole jets. This is another important parameter to understand black holes. We don't really know much about them because it is still a mystery. They are also called astrophysical jets. Black hole jets are thought to be powered by materials falling into the black hole. Theories suggest that these jets are a combination of positron-electron plasma. Now, you all might have heard of electron, but what is a positron? A positron is nothing but the anti-particle of an electron. Basically, the universe began with equal amounts of matter and antimatter. So basically, for every lump of matter, there is a certain number of antimatter. So the antiparticle of electron is a positron. In the same way, the antiparticle of a neutrino is an antineutrino. Jets are aligned with the spin axis of black holes. So as you can see in the photo over here, you see a jet in the upward direction. So there is not only a jet in the upward direction, it is in the downward direction too. These jets are linear and magnetic fields tend to keep them straight. Now, escaping from a black hole. I won't recommend you to go around a black hole, but if you are trapped around it, so this is the basic equation you must understand to explain it. So what happens is total energy is always a summation of kinetic energy and the potential energy. So in this case, the kinetic energy is given by half times mv square, and this is a gravitational potential energy g m by r. So g is the Newton's gravitational constant, m is the mass of the black hole. This is m. The small m is your mass, and the r is the distance of separation between you and the black hole. And the m over here is your mass, and this is the velocity with which you are moving. So in this equation, the right hand side is 0. So on substituting the values, if the right hand side is 0 or positive, you have successfully managed to escape. You don't need to worry about it. And if negative, you are still trapped under the gravitational influence of a black hole. But what happens in the black hole is its gravitational pull is so high that not even light can escape it. So the velocity of light is also not enough to escape it. So in order to escape a black hole, you have to travel with a velocity greater than the speed of light. So this is the basic equation for the escape velocity. And now let's convert the sun into a black hole. You can do it using some basic physics, but only hypothetically. In reality, it is not possible. So this is the equation we use, the same equation of our escape velocity. Over here, Rs is the radius of the sun, G is again a Newton's gravitational constant, Ms is the mass of the sun, and C square is the speed of light. So on substituting these values, the radius turns out to be 2.95 kilometers. So what it is trying to say is, if you try and squeeze the sun down to a radius of 2.95 kilometers, okay, so its gravitational pull will become almost infinite and it will be a black hole then. But the only problem with our sun is it is not massive enough to be a black hole. In order to be a black hole, you must have high mass. So our sun will not really be a black hole, fortunately. So recent enough, we had a big breakthrough in science. The first ever image of a black hole was captured in around April 2019. So it's a pretty big discovery. So this is the photo that was captured. The orange shiny thing that you see over here is the accretion disk, and the black thing you see is the black hole. So basically, in order to spot a black hole, you always have to go for the accretion disk. The first ever image of a black hole at the center of Messier 87, or you can say M87 galaxy, was published by EHT collaboration on April 10, 2019. EHT is nothing but the Event Horizon Telescope, large telescope array consisting of a global network of radio telescopes. Now, in order to observe black holes, you don't use optical telescopes because you don't really see them that easily. So, in order to spot a black hole, you need to go for radio telescopes, because radio waves, as we know, have the highest wavelength. So they have the potential to travel large distances. So we use a network of telescopes on the planet Earth, and we try and synchronize them to get a high resolution image of the black hole. It combines data from several very long baseline interferometry. This is the principle on which it works. Stations around Earth with great angular resolution. The array of telescopes creates an aperture as large as the diameter of Earth. So basically, the aperture is so large. Now, aperture is nothing but the opening of a camera. So if you have larger aperture, a high amount of light can enter your lens, and basically it can give you a clear and a high resolution picture. All the telescopes are in synchronism with the Earth's rotation. Now, in the photo, as you can see, these are the network of telescopes that we use, but these are all located at different locations. So what we have to do, the Earth is rotating every 24 hours. It is completing one rotation. So what is happening is these telescopes point in different directions at different points of time. So we have to synchronize them and see to it which telescope is pointing at the galaxy, at the black hole at a particular instant of time, and we have to sync it to sync it together in a supercomputer. So basically, the supercomputer accumulates all the data and give you the final output. So this is what they used to generate the image, and it was a big breakthrough for science, because till now it was always a mystery whether black holes are real or hypothetical. Some said it was real, and some people did not believe in such things. Now, I don't know if you knew, our Milky Way galaxy hosts a supermassive black hole called Sagittarius A star at its center. Its mass is approximately 4 million solar masses, and it is located approximately 30,000 light years away from us. Almost every galaxy hosts a supermassive black hole at its center. You won't believe our neighboring galaxy, Andromeda Galaxy, also hosts a supermassive black hole at its center. Scientists have been looking at almost all the neighboring galaxies, and they have found that there is a supermassive black hole at every galaxy they have seen. So this answers a lot of their questions. Most of the stars we see in the sky are binaries. So normally we see one star and we think that it is only a star in the sky, but sometimes there are two stars and we don't see the other one. So this was the case in Cygnus X1. The scientists could see the star, but they could not see the black hole. So the black hole was emitting a large amount of X-rays. So using X-ray astronomy, Paul Morden and Louis Webster were able to detect the black hole. Otherwise, we could not see it with optical telescopes. The laws of physics fail beyond the singularity. So we don't really know what lies beyond the singularity of a black hole. The space-time, as we know, is not defined beyond the singularity. For supermassive black holes, the tidal forces are much gentle at the event horizon than the forces around stellar mass black holes. So basically, if you want to go visit a black hole, always make sure it is a supermassive black hole, because if you go around a stellar mass black hole, the tidal forces will be so high that they will rip you apart in fractions of seconds. Also, you can move around black holes in innermost stable circular orbits. So these are called ISCOs, innermost stable circular orbit ISCO. So what happens is, around the radius, around the event horizon, the radius of these ISCOs is around three times away from the ISCO. So basically, around the ISCO, three times far away, you can revolve in these ISCOs and study the characteristics of a black hole. If you want to experience its tidal forces, you want to move around it in the accretion disk, you can see all those things and study those parameters. Although this is very much hypothetical, these are just mathematical formula based things, but they do exist. Now my references. So for this talk, I use data from NASA JPL, Jet Propulsion Laboratory, some from Wikipedia, then MIT website, Caltech, space.com, and I referred the International Journal of Astrophysics and some data from the Wire. So thank you, and with this I would like to end my talk, and all I would say is space has a lot to offer. So keep learning and keep sharing, because science can go all the way. Thank you.